Hello everyone, welcome to this Men&Mice webinar. My name is Peter Petersson, and with me today I have Karsten Strothman from the Men&Mice Professional Services team. And today's webinar is the second webinar in a trilogy called Rethinking Name Resolution in Local Networks. And the subtitle of this webinar is Local Name Resolution in Windows Networks. So please note that all attendees are on mute, but we encourage you to submit your questions through the GoToMeeting control panel. We're also recording the session, and you can find this webinar along with the slides at our website within a few days if you have to drop off by any reason. And you can also find recordings from part one of this trilogy or any previous webinars. You can find this at our website. So, Karsten, the audience is yours.
Thank you, Peter. So, hello everybody. This is Karsten, and today we talk about local name resolution in Windows networks. So last time we have discussed the naming options for DNS in local networks. And this time we look besides DNS. So we don't cover DNS here, but we cover two additional protocols that are available in Windows networks that can be used in local name resolution. The one is the LLMNR, which sounds like a disease, but it's actually LinkLocal Multicast name resolution. And like the name suggests, it only works in a single subnet. So that is good for some kind of ad hoc networking. And the second one is the PNRP, which is the Peer Name Resolution Protocol, which can also work in a local subnet, but can also work on a global scale. So when we take a look on these two protocols, how they work, and how they integrate in the overall Windows ecosystem. We start with the LinkLocal Multicast name resolution. And that provides serverless name resolution, meaning that there's no need for any central component, and it does name resolution inside the same local subnet. It works for IPv4 and IPv6 and has been documented in an informal RFC in January 2007, and the RFC number is 4795. Now, an informal RFC means it's not a real internet standard, meaning that it's not required for any machine on the internet to implement that. It's just documented here by Microsoft if like someone wants to implement that. And actually, like we will see in the last part of this webinar trilogy, that actually the Linux people, they have taken this RFC and implemented that on Linux as well. So on the wire, LinkLocal Multicast name resolution works very similar to DNS. Even the packet format is very, very similar. So if we do a packet capture with TCP dump or network monitor or Wireshark, something like that, we would see that the LLMNR packets flowing back and forth, they look very much like DNS. The big difference is that LLMNR works on port 5355, and it's using multicast addresses. So every machine that wants to take part in LLMNR communication will register itself on one of these multicast addresses, either IPv4 or IPv6 or both, and then it can receive requests from other machines in the local subnet. The LLMNR works only on short single label names. So it's very similar, therefore, to WINS and the old NetBIOS name resolution. So if we have a host that has a DNS name, windowspc.home.rpar, or any other subdomain and top-level domain, that machine can be just reached with his short name Windows PC. We can use LLMNR on the command line with all the command line tools that use the DNS Client resolver on Windows, because if because that DNS Client resolver will first try to resolve that name just normally via DNS. And if that doesn't work, it will fall back to LLMNR or NetBIOS wins if that is still available. So all command line applications should work, and also graphical applications will work, but be aware that some applications like web browsers, they assume multi-label host names, and they are confused if there's just a name without a dot in it. They see these single label names often as a search request, and I will show that in the demo how that looks like. In order to work around that with LLMNR single label names, you have to enclose the name in a proper URL. Like you have to write protocol http://Windows PC/, and that tells the browser, hey, this is a complete name. It's not a search term that I want to search at Google or somewhere else. Please directly connect to that machine. Availability. Every modern Windows system, no matter whether it is a client or server system, will send LLMNR requests to the networks. However, only systems that have network discovery enabled will also listen to these queries and will send answers. And on the server platforms, network discovery is usually disabled completely. So you can, sitting on or working on a Windows 2016 server, you can resolve LLMNR names, but nobody can resolve the server. Same is with Windows 10 and Windows 8 and Windows 7. If they are on a public network or a network designated for work, then network discovery is usually also disabled and must be manually enabled. Where it works is the home network. If you are in a home network, network discovery is enabled by default. You can use NetShell to look up the state of LinkLocal Multicast name resolution with NetShell DNS Client show state, and it will show us the query failure behavior. And this is a screenshot from a Windows 7 system. Actually, in Windows 10, this looks a little bit different, and we don't see this option in this output anymore. We have to go to the GUI to find out whether network discovery is enabled or not. But in Windows 7, and I haven't looked Windows 8, but maybe Windows 8 is still the same, you can see that in this case, there's a fallback to LLMNR and NetBIOS. If you see LLMNR as a security problem, and we discuss later on why that could be the case, you might want to disable LLMNR requests completely so that not even your machine sends the request. You can do that via a group policy, and that is the group policy, computer configuration, administrative templates, network DNS client. And then there's an option to turn off multicast name resolution. In the absence of a global policy, LLMNR can also be controlled using a registry key. And we see the path here, and we have to enable, or we have to maybe create a key called enable multicast of a type rec D word under that path. And we can put a value in there. 0 means disabled, and a 1 means enabled. In order to troubleshoot LinkLocal Multicast name resolution, that can be tested with the resolve DNS name PowerShell commandlet, and that commandlet has a -LLMNR only parameter. And we give it that parameter, it will only resolve the given name via LinkLocal Multicast name resolution and not via DNS or any other means. Because without that tool, all requests go to the DNS client, and the DNS client internally decides whether to resolve that name via DNS, LLMNR, peer name resolution protocol, or maybe any other protocol that is available. So now we try a little demo And I have a Windows 10 machine running here, and that is in the same local network as a Windows 7 machine. And both have LinkLocal Multicast name resolution enabled. And the Windows 7 PC is called Windows 7 PC, and the Windows 10 PC is called Windows 10 PC. So on the command line, I can just do ping Windows 7 PC. Yep, typo. And that should be enough to do the name resolution. So that name is not in DNS. And we see here it has resolved in the LinkLocal IPv6 address of that machine. That is because IPv6 is preferred over IPv4 in name resolution, and also Windows 7 PC doesn't have any global IPv6 address, so the LinkLocal IPv6 address was the only address available. If we want to force resolution of the IPv4 address, we can do so with ping -4, and then I look up Windows 7 PC. And it does the name resolution as well. Now I'm quickly switch over to the Windows 7 PC to start a web server there. So here we have the Windows 7 machine, and I need to quickly hide this console window here and then start the web server, which is just a simple web server here to for the purpose of showing the connection. And this here, this web server, listens to port 8080 on this machine, and I've just started the web server listening on that port. And now I go back to the Windows 10 machine, open the web browser, and now I try to connect to Windows 7 PC :8080/. And if all works well, we should see the directory contents there. And this is the directory content of one of the directories on the Windows 7 PC. So this worked because I typed in the whole URL. Let me just type in the Windows 7 PC :8080. So without the protocol part around it, if I press enter here, the browser will identify this as a search request and will send me here to Yahoo, because that is the default search engine for that Vivaldi browser I'm using here. So we have seen we can use command line applications, and we can use graphical applications to connect to hosts via LLMNR. Now, what is it with security? Now, LLMNR is not authenticated, very similar to the old plain DNS. So there's no DNSSEC or the like. The host sending the queries will just receive anything that comes back on port 5355 and will take that as the real answer. Now, that makes it really, really easy for an attacker, in which the attacker must be in the local network, of course, but if the attacker is there, makes it very easy to spoof responses. And that makes LLMNR very dangerous on public networks, like a Wi-Fi network, hotel or airport networks. If and their networks, all the clients are not separated, and if they can see each other over multicast. And there's a blog post from a pen testing security company that shows how this attack can be used to get credentials, maybe so that you can take over a Windows machine. And there's even on GitHub ready-to-use spoofing tools that can just spoof any name on LLMNR, or can even make that it will respond on any name that is being sent over or requested over LLMNR. So in this environment, it might be a good idea to disable LinkLocal Multicast name resolution. But in a controlled environment, like in a company network or a home network, LLMNR works just fine. So next is the PNRP, the Peer Name Resolution Protocol, and that is a more complicated protocol. It is a protocol designed by Microsoft, and even though the specification is open, so far, to my knowledge, only Windows systems, starting with Windows Vista, have implemented this protocol. Windows XP had an older version of this protocol, which is not compatible with the version 4 that is used since Vista. So basically, Windows XP machines cannot talk to Windows Vista and younger machines. Also on the server machines, the PNRP protocol is not enabled by default, not installed by default, but you can find it under features, and you can later install it on a Windows system if you like to use it there. PNRP requires IPv6 to work. It will not work in an IPv4 only network. However, a Windows system that detects that it is running on an IPv4 only network, and where some application tries to use the PNRP protocol, will try to create a Teredo tunnel, which is a tunnel IPv6 over IPv4 to make PNRP work. Even though PNRP only works over IPv6 as a protocol, it can resolve IPv4 addresses as well. Now, when I talk here over Teredo, you might know that Microsoft has shut down the Teredo service just 2 years ago. So why can that work if the Teredo service is shut down? The answer is it's not really completely shut down. Microsoft still operates machines, Teredo tunnel endpoints that are only for the purpose of making PNRP work. So it's not in the system, at least not in Windows 10, to be useful or to be configured to use Teredo as a global tunneling protocol for IPv6 over IPv4. However, if PNRP is started or any application requiring PNRP, then a Teredo tunnel is still being created. So PNRP technically is implemented as multiple distributed hash tables, meaning that the name and the IPv6 address of the client is being hashed, and that hash is or has a hierarchical relationship with its peers. And by intelligently walking down the hash and the parts of the hash, clients can figure out where in which part of the network, even in the global internet, a machine is available and can be reached. Every PNRP node that takes part in a cloud knows few addresses of its neighbors of the PNRP cloud. And by default, a local cloud and a public, which is the global internet PNRP cloud, exists. But it's possible, using NetShell, to create own clouds that have more limited scope. So maybe you can create a cloud that only works in your company and only contains the networks that are in your company's network. PNRP works with addresses, and these addresses are calculated from a human-friendly part, which is called a classifier, and optionally a cryptographic key, which is called the authority. The cryptographic key can be substituted by a 0, which means no keys being used. That makes the resulting name very human-friendly, because it then can be typed and remembered, but also insecure, because without a cryptographic key, the security of PNRP is very equivalent to classic DNS. Having the cryptographic key in the scheme, which is then hashed with SHA-1, we get more security, because then the receiving machine can verify that the machine claiming to be the named machine, the requested machine, is really the machine that is being configured by the administrator. So this is how a PNRP address is being constructed. We go from top to bottom, and we use the public cryptographic key, and that is being hashed with the SHA-1 hashing algorithm. And we can also use the human-friendly name, and that is being connected by a dot to the authority.classifier tuple. And that construct is called a peer-to-peer ID. And that peer-to-peer ID is then hashed again with the SHA-1 hashing algorithm, making the upper part of the PNRP ID, which is 128-bit the hash value from the peer-to-peer ID, and 120-bit that is derived from the IPv6 address of the host. And now that's the reason why IPv6 is mandatory, because the 128 bits called the service location here is actually the IPv6 address of the end host. Yeah. PNRP itself works on port 3450 for all the PNRP communication to the outside world. If you want to use LinkLocal communication, also port 1900 for the simple service discovery protocol needs to be open. The reason is here that PNRP requires some seed servers to learn the first peers it can make contact to. In the internet, this peer seeding is being done by 2 Microsoft servers that are in the internet, are resolved by classic DNS. But if you have your own cloud in your own organization, the Microsoft servers don't know about that. So you need to set up your own peer servers, seeding servers, and finding these servers is done with a simple service discovery protocol. And of course, if you have an IPv4 only network, you need to permit Teredo through your firewall somehow. However, IPv6 via Teredo is sometimes unstable. And if at all possible, native IPv6 is preferred. It just works better. So with NetShell, again, we can check whether the PNRP system is enabled and is working. The command here is netshell peer-to-peer PNRP cloud show list, and that shows the list of all the clouds that are available for PNM resolution. And by default, we have 2 clouds. One is the LinkLocal cloud, and the other one is the global cloud. And if they are in the state virtual, that means that the service is installed, the service is actually running, but it's not initialized. The reason here is that PNRP can be very chatty on the network. And you don't want a PNRP send a lot of packages through your network if it is not needed at all. So the clouds only become active once a service or an application makes use of PNRP. That service can be at the command line or the NetShell tools, or can be any application using the Windows APIs for PNRP. So in this second slide, we see the LinkLocal cloud active. So PNRP is working there, and the global cloud is alone. And this state of alone means that it has no connection to the outside IPv6 world. That most of the time is then a problem with the Teredo protocol. Or you have an IPv6 firewall that blocks the PNRP port. To show the Teredo status, there is a netshell command as well, which is netshell interface Teredo show state. And here we see the server name Win1710. That is the for the release, for the last creators release. It's for Windows 2017 release October 10, IPv6 Microsoft.com. However, even though this is being shipped with Windows 10, if you put that name into a Windows 8 or Windows 7 Teredo configuration, you can enable Teredo for these older Windows systems as well. Not that I would really recommend that, because Teredo is just broken, but you can try it out. So I talked about seeding the PNRP cloud, and on the global cloud, the systems are connecting to these two servers listed here, PNRP v2 IPv6 Microsoft.com and PNRP v2.1 IPv6 Microsoft.com. So these need to be resolvable in your network, and these need also be reachable over the PNRP ports. For the instance that a machine was disconnected from the network and hadn't really seeded its PNRP cloud, and you want to force reseeding, you can do so with netshell peer-to-peer PNRP cloud synchronized seed, and then the name of the cloud, which is usually global underscore for the global cloud. Now, how do we get our names in PNRP? PNRP doesn't auto-register names, so it's not that your machine's host name is automatically in the cloud and can be resolved globally. You have to explicitly put names in there. Registration of names can be done via netshell as well and through the Windows API. Netshell peer-to-peer PNRP peer add registration, and then the name of the service, and an optional command that will register the name in all clouds. So giving 0 as the authority and then dot and then the human readable name, that creates an easy to use name, but an insecure name. If you want to have a name that is more secure, you use the hash of a cryptographic key as the authority here. However, that is best being done through the APIs and not through netshell. There's a second option to put names into PNRP, and that is a tool that I wrote some 8 years ago called PNRP Beacon. You find the download link here on the slides, and that is a .NET application where you can put any names called topics here in the list, and your Windows machine will then start announcing these names in both the local and the public cloud. And if there's a peer being found, it also can show the peers, meaning all the machines that have the same name or use the same service name. And if a peer is being found, it also tells us the operating system running there, the host name of the machine, the remote machine, what kind of Windows, even service packets running there, and the CPU count. Now, this is not a function of peer name resolution protocol. That is a function of the PNRP Beacon program, because it puts all that data in PNRP so that it can be resolved. If you just register with netshell, all you have in the cloud is your name. So it's not that everyone outside can resolve your service pack numbers and the number of CPUs. Names that you register via netshell or PNRP Beacon are not persistent, so they are gone after a reboot. If you want to have a persistent name for your machine in the PNRP cloud, you can do so with Windows Internet Computer Name Service, which can also be controlled via netshell, and that is netshell peer-to-peer PNRP peer set machine name equals, and then your PNRP name, publish equals start, and auto publish equals enable. And that makes that one name automatic published whenever Windows is rebooted. That also means that your machine has PNRP enabled and the clouds are being initialized whenever you start. Something you may or may not want. The status of the Windows Internet Computer Name Service can be listed with netshell, peer-to-peer, PNRP, peer show machine name. And that will tell us that our machine has the name 0 Windows 10 PC and it being published as the name Windows 10 PC.pnrp.net. What is this pnrp.net thingy? We talk about this in a moment. It's a way to resolve PNRP names via DNS. The netshell command show names will list all the registered names on the host, including a lot of detailed statistics and information about the protocol. So if you want to know under which names your machine or maybe some of your applications are available, you can use this command. There are some built-in services in a Windows operating system that make use of PNRP. One is the home group service. Now, home group is a service where you can connect one or more machines or two or more machines over the internet, and you can share pictures and files and other stuff without needing to know the remote IP address. And that works over PNRP as well. The secret password that you get being shown and that you have to communicate to all the machines that should be part of the home group, that is actually the secret key that is being used for that PNRP address. Now, resolving names that are registered can either be done with netshell or the Windows API or through the Windows DNS Client. The Windows DNS Client intercepts all queries that go for a domain name with the domain pnrp.net. And these queries will never be sent to the real DNS system, but they will send to the PNRP subsystem. And that works best with these insecure names, meaning the authority is 0. So a PNRP name of 0.mywebserver becomes the DNS name mywebserver.pnrp.net. And that can be just resolved with any application, because normal applications, they just talk to the Windows DNS client, and if it is an application that can handle DNS names, it will take this DNS name, will send the DNS name to the Windows DNS client, and the client will redirect that query to the PNRP subsystem. If then an answer is coming back, that answer is being wrapped in a lookalike DNS answer and will be given to the application to work with. So resolving a PNRP name with netshell is netshell peer-to-peer PNRP peer resolve and then the name. Now in netshell we have to give the PNRP ID name, which is 0. and then the name we have given the service. Or we can use PNRP beacon for that and put the name in there. If we use beacon, we just put in the plain name without the 0. in front. In the log, PNRP beacon will show us the PNRP ID that is being created and also the DNS name of the service. And it also registers new endpoints for port 80. So these names can then directly be used for a web service to make the web service available on the internet on port 80. There's also a PNRP traceroute command that can be used to list all the PNRPers in the name resolution. So if we want to really know what happens if a peer name resolution protocol name is being resolved, the traceroute command under the PNRP context will make that visible. So now we have a short demo, and again go back to my Windows 7 and Windows 10 systems here, and I start the PNRP beacon program. on the Windows 7 system. The system seems to have become unresponsive, so let's try if I can do the same on the Windows system. Starting the beacon there. So here it's starting. And that is the .NET application. When you start that the first time, it might then install and download the whole .NET runtime environment. So here I put in the name of Windows 10 PC, and that has been then immediately registered in the system. And it shows me here that the DNS name would be Windows 10 PC.PNRP.net, and it already has found other endpoints that are using that IP address, having an IPv6 address, having a LinkLocal IPv6 address, and having an IPv4 address. So now I'm switching over to the Windows 7 system. Unfortunately, that seems to be gone. A little moment. Yep, host is down. That's unfortunate. The demo gods are not good to me to say. So it seems to be the Windows 7 machine is down and not reachable anymore. So I can't show you that. So what I wanted to show you is that on the web browser, was just typing in Windows 10 PC.PNRP.net, I could also reach the web server that is then running on the Windows 7 PC. So I will try to create a video on that demo, and we will upload that video together with a recording of this session so that you have the ability to see the demo live later on. Not live, but recorded later on. So how about the security of PNRP? The security of names without authority, that is without a public key, are similar to classic DNS. They can be spoofed from anyone in the PNRP cloud. And that actually is intended by the protocol, because the idea is that if there are multiple hosts that announce the same name, they belong to the same service. And if a client connects to that name, it works like any cast, meaning it connects to any one that is being found, which is usually the first one that is found in the peer-to-peer name resolution. If you use the PNRP name with the public key, that is protected against spoofing. However, while spoofing that name protected by a cryptographic key is hard, it's not entirely impossible, because we are using SHA-1 hashes here, and SHA-1 is known to be not 100% collision resistant anymore. So with the enough computing power, it's possible to create collisions in SHA-1. So theoretically, it would be possible for someone to spoof an address, but still, it's probably still a lot more secure than classic DNS and other name resolution systems. It is, however, recommended to have additional authentication on top of the name resolution. So meaning when you connect with some service protocol to the remote machine, have the remote end authenticate by some means, either a TLS certificate or something else. So that was our covering of the alternative Microsoft name resolution protocols. Before we come to the question and answer part, let me tell you a little bit about the Men&Mice training. We now have a tentative schedule for the training for the international English language trainings for 2018. 2015. We're starting at the US East Coast in February, then coming to Europe in April, and then in May we are on the West Coast and being back in Europe in June. And we will offer at these dates the DNS and Bind Fundamentals, which is a 2-day class, the DNS Bind Advanced, which is a 3-day class, and that can be combined to a 5-day DNS and Bind week. And at some of these dates, there will also be the availability of the DNSSEC and Bind class, which goes more deeper into how to do the DNSSEC key rollover and all that stuff. We also have the trainings in Germany again, in German language, and there we start in March with the DNSSEC and Dane training, and the 3-day DNS and Bind in April, followed by the 2-day DNS security class. And then we have the same in June and August again. The next webinar, which will be the last of our triology, will look at the local name resolution in Unix systems. We will take a look at Linux, FreeBSD, and macOS, iOS, and we'll see how multicast DNS is implemented there, and also how systemd now implements LinkLocal Multicast name resolution, how that can interoperate with the same protocol that we have seen today on Windows systems. I would be very happy to see you again there on the Wednesday, the 29th of November. So that concludes this webinar. Do we have any questions?
Carsten, no, we don't have any questions yet, but we can maybe give the attendees a minute or two to think of their questions. So Carsten, with Internet of Things up on us, somehow we need to put names on all these new devices. Are we going off track by inventing these new ways, for putting names on things rather than using DNS itself?
Yeah, I mean, these Internet of Things devices, they need to be maintenance-free, and setting them up should be as easy as possible. PNRP, the peer name resolution protocol, would be a good fit for them. However, I don't see that really used in that space, partly because Microsoft is not really a name in the embedded space, not anymore. And most machines running Internet of Things are some kind of Linux or one of the BSDs, and they don't have these protocols, at least not on the global scale. They have LinkLocal Multicast name resolution, but yeah, that might work for the local network, but not on a global scale. So I fear that the vendors will invent their own incompatible protocols.
Well, that is not the optimal solution, I would say, but we'll see. So there are no questions yet. I think if there are no questions, Carsten, I think we'll just put an end to this webinar today. Anything else you want to address now?
No, I just want to say it's maybe interesting to test out these additional protocols that are available. So far, I haven't seen them really being used, although they are built in Windows for many, many years now. PNRP is now in there for more than 7 years. LLMNR is even older. So in some situations, they might be a good replacement for DNS, where DNS is not a good fit. Of course, it doesn't make sense to replace DNS on a global scale with these protocols, but in local networks, these can be very helpful.
Very good. Let's then end this webinar by saying that we agree that nothing replaces DNS. So
right.
yeah. That being said, I would like to thank everyone for attending, and thank you, Karsten, for presenting today. And we're looking forward to seeing you all here at the next webinar. So until then, have a good time. Thank you.
Thank you. Bye-bye.